I certainly hope so. Okay, so last time I gave some introduction to cluster algebras, and I told you about a lot of different types of cluster algebras. Some of them I mentioned were acyclic, finite type, finite mutation type, and then I mentioned surface type, which I didn't define, that I said would be the subject of some later lectures. Okay, so still that would be the subject of some later lectures. But for now, I want to talk about finite type cluster algebras. And I must admit that, I mean, the way I'm going to give this lecture, I won't prove that the finite type cluster algebras are what I say they are, but I'll instead give you some motivation on why we should care. Okay, so yes, the proof is quite long and tedious, and there's not much, I mean, it's not super enlightening. So. Okay, so before I start with this, I want to clarify something. I mean, I think there's been a lot of back and forth between quivers and matrices and like what is going on. Okay, so I used the story with quivers last time, so I want to kind of talk about how you can move back and forth between quivers and matrices. Okay, so this is not about this yet. Okay, so I'm just doing some side thing. So if I have a quiver, maybe with frozen vertices. Remember, these are the ones that I'm not allowed to mutate at. So say maybe this one as an example. So I gave this one last time. I called it the dreaded torus. And I said I encouraged you to try to play with this one and see that you get a finite number of quivers, that this cluster algebra is in fact a finite mutation type. And if you didn't see last time, I don't know if I actually drew it or not, but I meant for this one to be frozen. Okay? Maybe I wrote a circle, or maybe it was hard to see, but yeah, this is meant to be a square. So just numbering the vertices. So if I have such a quiver like that, I can form some matrix from it, which is called the adjacency matrix of that quiver. Okay? So from this, I can get a matrix, and this matrix is going to be a skew-symmetric matrix. At least what part of it will be. So I'll say this in 1 second. So let's get a matrix from this. So I'm going to label the rows by these vertices, and I'm going to label the columns by the mutable ones. So I won't have a column 5. Okay? All right. So now the adjacency matrix just keeps track of these arrows. Okay, so this is called the adjacency matrix. So there are no loops in my quivers, which is not like the last talk, but there are no loops in my quivers, so there will never be an arrow from a vertex to itself. So I'll have zeros from 1 to 1, 2 to 2, 3 to 3, 4 to 4. Okay. Now from 1 to 2, I have one arrow. So from 1 to 2 in the 1 row and 2 column, I put a 1. Okay. And in the 2-1 entry, I sort of see an arrow going in the opposite direction. So I put a -1 there. Okay. So I continue in this way. So what about 1 and 3? So I see an arrow, but it's oriented in the wrong direction. So I make a negative entry. And from 1 to 4, I see an arrow in the correct direction, and there's one such arrow. Okay, so 1, 3 was -1, so 3, 1 should be +1. Okay, it's going in the correct direction. And I continue this, so 1, 4 is 1, 4, 1 is -1. Okay, and if you continue this, I'll just write what the answer is. So I get 2 and -1 here, I get -2, I get 1, I get 1, -1. Okay, and then in this last row, it's just how this frozen one is connected to the mutable ones. Okay, so 5 is connected to 1 with 1 arrow. 5 is not connected to 2 and 3, so there are 0 arrows. And 5 is connected to 4, but in the wrong direction, so I have a -1. Okay. So you can build an adjacency matrix from a quiver, and you can go back and forth. Okay. So if you have this, then certainly you can build this. Okay? And this matrix, so if I split it into two pieces, this is called the principal part. Okay? The principal part. And this is everything else that has to do with the frozen vertices. Okay? Then it turns out that this principal part is a skew-symmetric matrix. Okay? So this is a skew-symmetric matrix. That means that if you take its transpose, you get the negative of the matrix. Okay? Okay. So I want to tell you about one more step in this direction. So there's a slightly more general story. So there's a more general story where instead of quivers, I consider something called valued quivers. So I think Tomoki talked about skew-symmetrizable matrices. So you can also see these in the quiver language as well. Okay? So I just want to make the dictionary. All right? So if I have a skew-symmetrizable matrix, and Tomoki gave this definition. So for example, 0, 1, minus 2, 0. Okay? Just this, here's an example. Then I can associate to this something that's called a valued quiver. So this is a quiver where if there's an arrow between the two vertices, maybe they can't agree about how many arrows they see. Okay? So like if there's an arrow coming out of this one and going, if there's some number of arrows coming out of this one and going into this one, maybe this one sees only one coming out and this one sees two coming in. That's what valued quiver means. Okay? So I'm going to write these numbers in a different color because I'm not labeling the vertices, but I'm telling you the value. Okay? This quiver, this vertex sees one arrow coming out and this one sees two coming in. Okay? And you can imagine, like, if I try to write down the adjacency matrix in the same way that I did, this is what I get. Okay? So that's all I wanted to say. Just to, like, if you're trying to sit there with all of the notes, I just wanted to try to make sure we're all on the same page. Okay. And by the way, there's also, as Tomoki said, like I did this mutation on the quiver side, and he defined a mutation on the matrix side, but these are the same story. Okay, so you can do it on both sides. Okay, so let me start with this finite type cluster algebras now. So I want to classify these guys. I want to classify finite type cluster algebras. And as I said, so the spoiler alert is going to be, well, here they are. Okay? So I didn't tell you to close your ears, sorry. So that's what the finite type cluster algebras are, and I'll be more explicit later. Okay? But I want to tell you another thing, just to sort of motivate this, I want to tell you another thing that these diagrams classify. Okay? And these are going to be called root systems with some kind of adjectives. Yep. Oh, in each of these, they're in mini vertices, whatever n is in this. They're labeled something n, and the n means the number of vertices in these pictures. And this dashed line means, you know, I have vertex 1, 2, 3, and then it continues along in this way, and this is the last vertex n. Okay? Yeah. In this case, yeah. Yeah, I mean, actually, it's better to see it in. I mean, I think you should look at Tomoki define the mutation in terms of the matrix. So I think you should work. It makes more sense, I think, to work on the matrix side. Yeah. You can, but I think the matrix is more clear. Okay, so this is going to take me through something called crystallographic root systems. Crystallographic. So I have to go a little bit faster today, but you should still ask me questions. And if I feel that I have to go faster, I'll just tell you, we'll talk after. Okay? Okay. So before I get to crystallographic root systems, I want to talk about reflection groups. Okay, so reflection groups. I somehow lecture very slowly. Okay, so reflection groups. So I'm going to start with V being a real vector space. And I'm going to start, so on this real vector space, I'm going to have some nice bilinear form. So this is a map from V cross V to the real numbers. And I want it to satisfy some properties. So I want it to be positive definite. So this means that if I take any two vectors inside V, then I get my value is positive. Okay? If I pair the vector with itself. Okay? Positive definite, symmetric. That means the pairing of alpha and beta and alpha are equal. And bilinear. So that means it's linear in both positions. Okay? Yeah, alpha is not 0. Yeah, otherwise I'm in trouble. Yeah. Okay, thank you. All right, so an example of this is Rn, and I can take the usual dot product, okay, for this. The usual inner product. Okay, and once I have one of these positive, definite, symmetric bilinear forms, I have a notion of length, and I can talk about angles between vectors and all these sorts of things. Okay, so let me remind you, you've probably seen these before, but the length of vector alpha which I'll write like this, is the square root of the inner product of alpha with itself. Okay. And the angle between two vectors you can get by, there's some identity that says that the inner product of alpha and beta is the length, this length of alpha times the length of beta times the cosine of the angle in between. So this is how you can get the angle. Okay? And of course, if this angle is pi over 2, we say they're orthogonal. Okay? So almost done with this recap of linear algebra. So a linear map, phi from V to V, is an orthogonal transformation if this map preserves this bilinear form. Okay. Good. So, I mean, this means that phi of A comma B is the same thing as, taking the bilinear form and then taking the map is the same thing as taking the map and taking the bilinear form. Okay. So this will allow me. Okay. So first, I want to talk about now the group of all orthogonal transformations. And here the operation is just composition. Okay. So I'm going to write O of V like that. So now I'm ready to give you the definition of this reflection group. So first I'll tell you what a reflection is, and then I'll tell you what a reflection group is. So on this vector space, I can talk about a reflection. So reflection on this vector space V is a linear map. I'll call it S from V to itself. such that the following two conditions are satisfied. So this map should fix a hyperplane pointwise. Okay? So I'll tell you what this means. S fixes a hyperplane pointwise. So hyperplane just means it's a linear subspace that's one dimension lower than V. Okay? So if I'm in Rn, it's an n-1 subspace, an n-1 dimensional subspace. Okay? And the second thing is, S reverses the direction of any normal vector to the hyperplane that it fixes. So let me show you a picture. So here's an example. Okay, maybe not really an example, but an illustration of this. Okay? So I want to tell you what a reflection is. So this reflection fixes some hyperplane, pointwise. Okay? So I'm lying in some big vector space V, and I have this hyperplane, which I'll call H sub alpha. Okay? And this reflection is supposed to, if I pick a point on this hyperplane, it's not going to do anything to that point. The point's going to stay there. Okay? Now if I pick a normal vector to this hyperplane, let's call it alpha, then what this reflection does is it reverses the direction. Okay? It just flips this. So it's a reflection, really what you think it should be. Okay? So it sends this guy to the negative of it. And I'll write it like this. Okay? It's the reflection corresponding to along the hyperplane perpendicular to alpha, and what it does to alpha is it sends it to this vector. Okay? So there's a formula for these reflections. Okay? So there's a formula. So let's say, so the formula is going to be like this. It's going to say S alpha of beta. So this is some reflection through the hyperplane perpendicular to this vector alpha. And beta is just some other vector. Okay? So the formula to see what it does to a vector is beta minus 2 times the inner product of alpha with beta over the inner product of alpha with alpha times alpha. So let me try to, at least show you that this makes sense. It's a projection. Yep. So, but I'll check this. So by the definition, what is this supposed to do? If I pick a vector on the hyperplane, nothing happens. And if I pick one perpendicular to this hyperplane, it's supposed to flip it. Okay, so I'll just show you by this formula, this is what happens. Right? So say beta is inside, it's on this hyperplane. Okay? Then what do I get? So when I use this formula, S sub alpha of beta, so it's beta minus, okay, so if I'm on this hyperplane, then this dot product is going to be 0. Okay, because these are perpendicular. All right? So I'm going to get 0 here in this top part. So I just get beta. So what I said is it doesn't do anything to that vector on the hyperplane. Okay? And you can see that, if beta is equal to alpha, so if you pick this guy, then what you'll do if you go through the formula is you get negative alpha. Okay? So I'll let you check that. Any questions so far? Okay. So you understand what reflections are. I mean, there's all kind of linear algebra mumbo jumbo, but reflection, I mean, like the intuitive idea is reflection like you might think. Okay? Up to scale, yeah, that's right. Yeah, yeah. Mm-hmm. So definition, a reflection group is a subgroup of the group of orthogonal transformations generated by reflections. So I'd like to do an example now. Okay? So let's look at the symmetries of a triangle. Okay. So just checking how much time I have. Okay. So I should stop at 3:45. Okay, okay, sounds good. Thank you. Yeah. All right, so example 1. So I want to do the symmetries of a triangle. Okay? How many people have taken like some group theory type class? Like where you study symmetric groups and dihedral groups and stuff like this? Okay, good. Very confident. So symmetries of a triangle. I want to do an equilateral triangle. Equilateral triangle. Okay, so I'll draw some picture. And I'll do my best. You know, of course, I have to break out the straight edge and compass if I want to, you know, do a good job. But okay, so here's an equilateral triangle. And the symmetries of this thing, well, I can rotate the thing, okay? Or I can reflect through a bunch of lines, okay? So I'll draw these lines that I can reflect in blue. So there's a line like this that if I reflect, I get the same thing. Okay, so I'll call this H, the hyperplane. So my board is R2, and a hyperplane is 1 dimension down. So it's a line. Okay, so that's a reflecting hyperplane. And there's a line like this, and there's a line like this. Okay, so good. So I'll draw this. All right. So I'll call this one H alpha 2 for some reason that will become clear later, hopefully. And I'm going to draw the last one. All right. And I'll call this one H alpha 1 plus alpha 2. I'm just naming it something for now. Okay? It'll become clear later. So the point is that you only need reflections through 2 of these hyperplanes to generate all of the symmetries of this triangle. Okay? As long as I have reflections through these 2 things, I can get all of the rotations, I can get the reflection through this one. Okay? So you should try to convince yourself of this if you don't know this already. But I only need these 2, reflections through these 2. Okay? So this generates the symmetry group of this thing. Okay? So good. So great. And this is, I mean, the collection of all symmetries of this is exactly one of these reflection groups, because it's generated by these 2 reflections. Okay? So here, the symmetry group is a finite reflection group, meaning it just has a finite number of elements. It's a finite group. And it's generated by any of these two reflections through two of the hyperplanes. Okay? Good. So this is called the symmetric group on 3 letters, or the dihedral group of order 6. Okay? Okay. So now I'd like to classify these finite reflection groups, okay? And the point is that you can classify a bunch of similar things. You can classify finite reflection groups. You can classify finite type cluster algebras. You can classify something I haven't defined yet called root systems, okay? And all of these have the same classification, which have something to do with these pictures. Yeah, I haven't gotten to this, but I will. Yeah. So yeah, but I should say that B2. I mean, one part I should clarify is that if you have B2, then you don't have this side. Like it starts from, you just have this. Okay. So you sort of need enough vertices so that you have this funny arrow. But I will explain it. Yeah. You should not think of these as quivers yet. So don't think of that arrow as, I mean, like all of the other edges except that one at the end are unoriented. So don't think about them as quivers yet. I'll try to make it more clear, but right now they're just graphs. Okay, and I'll tell you what they have to do with cluster algebras in a bit. Yeah, so somehow I just drew these on the board because they take a lot of time, but don't let it confuse you yet. Okay, so I want to talk about these root systems. So out of these reflection groups, I can build something more combinatorial called a root system. Okay? So a root system is a finite subset. This is a finite root system. So it's a finite subset. I'll write it with this capital phi. Okay? It's a finite subset phi of non-zero vectors in my vector space V, satisfying the following two properties. So the first property is that for every element in this set, oh no, oh, okay, I thought I was out of time. Okay, so for every element in this set, so okay, I mean, a subset of this is some collection of vectors, so I can take the span of those vectors, okay? So the span of a single vector is just like all scalar multiples of it, all non-zero scalar multiples of it. So it's the line through this thing. So the span of alpha intersect this collection is just the vector and its negative. Okay? So what that's saying is if I include a vector, then the only scalar multiples that I have is the vector and its negative. Okay? And the second property is that for every two elements inside the set, for every two roots, so elements of this are called roots. Every element is called a root. The reflection through the hyperplane, where this is the normal vector, of beta, this reflection stays inside of this set. Okay? Okay, good. So let's go back to this example right here. So I want to write down a root system corresponding to the picture. Okay? So let's think about the definition. So I have these reflecting hyperplanes, and I want to think about the vectors that are perpendicular to these reflecting hyperplanes. Okay? So let's sort of draw those first. So this hyperplane, I have some vector perpendicular to it, which I'll call alpha 1, the same label as this. Okay? And I'm going to draw this in the perpendiculars, the orthogonal vectors to all of these hyperplanes. So for this blue line, I draw this vector. Maybe a little bit longer. I want to try to draw them so that they have the same length, but it's difficult. Okay. All right, so I have this, and I should, I can also draw this one. Okay. But I can also use these properties. I mean, so the first one says, like, if I have these orange vectors inside here, then I should also have their negatives. Okay? So I know I should also have this vector. And I should have the negative of this one. Okay? And now this one says that if I reflect, I should also include the vectors that I get inside of my set of roots. Okay? So this one, let's see. So I think this one, if I reflect along this hyperplane, I get something that points out like that. Okay? So I'll get two additional ones through these reflections. I mean, as long as I get one, I have to include its negative. So this is alpha 1 plus alpha 2. And this is negative alpha 1 minus alpha 2. Okay, so this is a root system. Okay, and this is called the root system of type A2. Yeah, so which vector space this lives in, I mean, you can, yeah, so with this abstract definition, so the point is like, okay, so these root systems are going to be classified somehow by these diagrams. And from these diagrams, they tell you, these diagrams sort of tell you information about the angles that you have between these vectors. Okay, but then you have to explicitly, for each of these diagrams, you have to explicitly construct such a root system. So you have to tell me a vector space with some vectors in coordinates that like gives you this Dynkin diagram. So yeah, but I don't want to be too, right now I don't want to say too much about the lengths of these vectors and stuff like that, but there is an explicit construction of each one that realizes these. What's that? Yeah, that's right. Yep. So this is the root system. So the root system of type A2. So somehow this picture is going to correspond to this picture. I only have two vertices. Our favorite, like I called it the A2 quiver last time. So somehow all of this notation is going to match up in time. Okay. Good. Any other questions? Okay. So good. So, I mean, I haven't been completely precise, but maybe I've given you an idea that if I have one of these finite reflection groups, so a group that's generated by reflections, a subgroup of orthogonal transformations that are generated by reflections, then I can build a root system like this. Okay, and I can go the other way. If I have a root system, I can build a reflection group. Okay? So if I have a root system and I want to build a reflection group, I just take the reflections through all of those roots. Okay? So any questions? Yes, so the vial group is, I have to add some other condition called, it has to be a crystallographic root system, which means that I require these, this quantity here to all be integers. When this quantity is if I require this for every root alpha and beta to be an integer, then what I get is a crystallographic root system, and those ones give you the vial groups, which come from the simple Lie algebras. No, I think they're negative. Yeah, no, I think they're negative. Yeah, the product of any two such quantities is positive, and like saying that it's an integer means it's only 0, 1, 2, 3, or 4. I'll mention that. Yeah, I'll mention that too. Yep. Okay. Maybe I should do one more example. I should just mention one more example like this. So this one is called the B2 root system. Okay? So it's like corresponding to that second picture there. Okay? Okay, so for this one I'll just draw the picture. So this is the symmetry of a square. All right, so I have a bunch of reflections that I can do. Okay, so I'll call that H alpha 1. I'll call this one H alpha 2. And I'll call this one H alpha 1 plus alpha 2. Okay, and I'll call this one, this is another one, another reflection you can do. So this is H alpha 1 plus 2 alpha 2. Okay, so these are a bunch of reflecting hyperplanes. And now if I draw the vectors that are perpendicular to all of these hyperplanes, I actually get a picture of all the hyperplanes again. Okay, I get some vectors on all of these hyperplanes. So like for this one, the vector that's, I'll draw them of this length. This is the vector I'll call alpha 2, because it's perpendicular to the hyperplane H alpha 2. Okay, and I'll do this for all of them. So here's hyperplane alpha 1, so I'll call this one alpha 1. And I'll continue this picture. So I get one for each one of these, right? And this is the root system of type B2. This one's the negative of this one. Negative alpha 1. This one's the negative of that one. So this is negative alpha 1 minus alpha 2. And this one is the negative of that one. And that's the negative of alpha 2. Okay, so this is called the B2 root system. So I just wanted to show you some examples. Okay. Do I need the distinction? Oh, right. So it has to do with the lengths of these vectors. Yeah, that's right. Yeah, that's right. In fact, they give you the same reflection group. They give you isomorphic reflection groups, but they're just a relabeling of these root systems. Okay, so yeah, so what Amihai was saying was that these two are pretty much the same if you only have two vertices for sure. Right? They're pretty much the same all the time. So they give isomorphic reflection groups if you look at these two root systems, the B2 and the C2 ones. Okay, so let me talk about simple roots now. And I want to keep this picture. And I might, erase this one later, but I certainly want to keep this one. So another reason I'm talking about all these root systems is I think people will use like positive roots and stuff like this later on in the lectures. So simple systems or simple roots. So definition. So some subset of these roots are going to be called simple. A simple system going to write it as delta for our root system phi is a basis of the span of the root system consisting of elements, so consisting of roots such that every root inside phi in my root system can be written in a nice way. So it's a collection of roots so that I can take any root and write it as a linear combination in a nice way. So in a nice way, I mean I can write it as a non-negative linear combination of elements in this set, or a non-positive, linear combination of elements in here. Okay? So the elements inside of a simple system are called, the elements of this are called simple roots. All right? And the ones that can be written as a non-negative linear combination are called positive roots, and the ones that can be written as a non-positive combination are called negative roots. Okay? So these such ones are called positive roots. So maybe I'll trying to figure out what to do with the board. So these are called positive roots. And we write the set of them as phi upper plus. Okay? And these are called negative roots. And we write this as phi superscript minus. I want to keep this example. I should add one more definition. This is a set. The size of this set is called the rank of the root system. Okay? So the cardinality of this set, that's what we call the rank of my root system. Okay? So let's go back to this example of symmetries of the triangle. Any questions? Okay. So let's go back to this example. So I should mention that there are various things that, so the first thing, like, given a root system, does a simple system exist? Does a collection of simple roots exist? That's not obvious, okay, but it's true that they always exist. Secondly, there's not one choice of simple system, okay? So I talk about positive roots and negative roots with respect to some simple system, okay? So in this example, if I pick my simple system to be alpha 1 and alpha 2, then I'll write down what the positive roots and the negative roots are, okay? So in example 1, so if I choose my simple roots to be alpha 1 and alpha 2, in this picture, then the positive roots that I get so it's the guys that can be written as non-negative linear combinations of alpha 1 and alpha 2. So the orange ones are my roots. So I mean, alpha 1 works, alpha 2 works, and alpha 1 plus alpha 2 works. Okay, and the negative ones, all right, so it's negative alpha 1, negative alpha 2, and negative alpha 1 minus alpha 2. Right? Good. And if I chose a different simple system, then there's this nice fact that, I mean, the coefficients of my positive roots are still going to stay the same, okay, in terms of that new simple system. Okay? Should I show you? Or is it okay? What's that? Yeah, so what I mean is, so choose a different simple system, say, okay? So maybe I choose, I'll call it beta because it's different. So let's choose my first simple one to be alpha 2, and let's choose my second one to be negative alpha 1 minus alpha 2. Okay, so to be a simple system, I have to show you that I can split the roots so that they're either in positive linear combinations or non-positive or non-negative, right? So here's how you do it. So beta 1, beta 2, so these two guys, and beta 1 plus beta 2 is also a positive root. So if you add these two, that's also a positive root. Okay? And then for the negative roots, negative beta 1, negative beta 2, negative beta 1, minus beta 2. So what I'm saying is that these coefficients are the same, even though I've picked different simple systems. Okay. Yeah, that's right. There's something called a vial chamber, and yeah, that's the idea. Yeah. That's right. Yeah, there's a lot to this story that I'm not saying, but you're absolutely right. Okay. Any other questions? So, okay. So Ashish asked me the question about what is vial group in this case, where do the vial groups come up? So I want to impose an additional condition on my root systems, which is they'll be called crystallographic root systems. And as I said, it's the one where I require this scalar popping up in the reflection to be an integer. Okay? So I think I'm going to erase this picture. Yep. So I want to talk about crystallographic root systems and Dynkin diagrams. So by the way, these things are called Dynkin diagrams. Okay. So definition, which I've said in words, but I want to write it on the board. A root system phi is called crystallographic if this quantity 2 times the inner product of alpha and beta over the inner product of alpha with alpha, so we've seen this before in this reflection formula, if this thing is an integer for every pair of roots that we have inside of our root system. So this condition severely restricts the root systems that we have. Okay, so this places this inner product of alpha with beta has to do with the angle in between. It has to do with the length of the vectors and the angle in between. Okay, so it severely restricts the sort of angles that we can have between our vectors and root systems. Okay, so we're really restricting the sort of root systems that we can find, and it turns out that we're going to have exactly these. And I'll tell you how to get these graphs in a second. So this severely restricts the possible angles between vectors. Okay. So I just want to make an observation to show you how it really restricts these angles. Okay? So let's say phi is now a crystallographic root system. Okay? So this is a crystallographic root system. So it has these three conditions, one of which is that these things have to be an integer. And delta is a simple system. So it's a collection of simple roots. So I'm going to call these alpha 1, alpha 2, through alpha n. So just to remind you of the terminology, the rank of my root system is n in this case, because I have n simple roots. And I'm going to introduce some shorthand, because this thing is annoying to write all the time. Okay? So my shorthand is going to be, I'm going to write A, this is not alpha, just A sub ij, is going to be this scalar where I put the pairing of alpha I with alpha j over alpha I, alpha I. Okay? So we should notice that, well, this crystallographic condition is telling me that all of these have to be integers. And if I have two integers and I multiply them, I still get an integer. Okay? So the product of any two of these such numbers is still going to be an integer. So A sub ij times A sub ji, this is going to be an integer. Okay? So let's write out what this is. And it turns out that, these sorts of products are going to encode the edges inside of that graph. Okay? So I'm just writing out the formula. I'm really writing this again. So if I recall that this inner product of alpha I with alpha j is the length of alpha I times the length of alpha j times cosine of the angle in between, then what I get is, and these are the length of alpha I squared and the length of alpha j squared in the denominator. So what I get is 4 cosine squared of the angle in between. Okay? So that's what I get when I do this computation. And the point is, this thing is an integer, right? Because these two are integers, so the product is an integer. Okay? But cosine squared is between 0 and 1. Okay? So 4 cosine squared is between 0 and 4. And the integers between 0 and 4 are 0, 1, 2, 3, and 4. Okay? So what I'm saying is that when I take this product, I get 0, 1, 2, 3, or 4. Okay, so this product is inside the set 0, 1, 2, 3, or 4. Okay? Okay. But I claim that, I mean, this 4, we already sort of know something about that. If 4 cosine squared theta is 4, then cosine squared theta is 1. Okay? So it means that the angle is either 0 or pi. Okay, but that can only happen with a vector and it's negative. Okay, so that's already one of the conditions in our root system. Our root system said we have to have alpha and it's negative for every root. Okay? So if I want to think about the possible angles between roots in my root systems, I don't need to think about this one. Okay? Because that only happens with a vector in itself. Okay. So I sort of won't think about this one. So now I'm ready to define for you these graphs. Okay? Yeah. Yeah, so, okay, yeah, what's going on with 4? So 4 cosine squared, so if 4 cosine squared theta is 4, then cosine squared theta, so I divide by 4, I get this is 1. And then theta has to be 0 or pi, so that only happens in our root system when I take a root, and I'm required, if I have a root, I'm required to have its negative. That's one of the things that a root system requires. So if I have 2 different roots, it'll never be this case where I get 4. This can only occur when I have the same root. There's one root and it's negative. Okay. These. Yeah. 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 Mm-hmm. Yeah, I mean, when I say what the edges are, it'll be clear. Okay? So, okay, good. So let me tell you the definition of Dynkin diagram. Oops. Good. So the Dynkin diagram of a crystallographic root system means even define Dynkin diagram, you kind of need it to be integers. Okay? Because these integers tell you how many edges you have. So I want an integer number of edges. Okay, so the Dynkin diagram of a crystallographic root system is a graph with vertices. Maybe I'll say vertices 1 through n, one of these for every simple root. Okay? So here I'm thinking of a rank n root system. One for each simple root. And my edges, the number of edges that I have are exactly these products. Okay? So I have Aij times Aj many edges between vertex I and vertex j. This many edges between vertex I, and vertex j. Okay, so I know in these diagrams, just by this sort of computation that I just did here, that if I take 2 different vectors, 2 different vertices inside of that diagram, then these are the number of edges that I can have. 0, 1, 2, or 3. Okay? So now maybe it's clear except for these arrows at the end. I haven't told you about these arrows at the end. But except for these arrows, it's clear how to get these diagrams if I give you a root system in advance. No. Oh. The vial group, this reflection group, takes any simple system to any other simple system. It acts simply transitively on these simple systems. Okay, so the last one is, the last condition I'm going to write tells you about these arrows. Okay? So if the inner product of alpha I with itself, which is the square of the length of alpha I, so this is about the length of alpha I and alpha j. If this quantity is bigger than the same thing of alpha j with itself, then I want to orient my edges from I to j. Then I orient those edges from I to j. So because, I mean, these are not oriented, it means that they're the same length. Okay? So like I showed you this example of B2. I drew a root system of type B2. And as Amihai said, C2 is very similar. The only issue is that, I mean, these are oriented in different directions because I'm just changing the length of these roots. But they give isomorphic reflection groups, these two. All of these are different except B and C, they give isomorphic reflection groups. D only 4 and above. Yes, but right. Yeah, I was careful. Okay, so in my remaining few minutes, I think what I'll do is, everybody clear with this kind of, like, how do you get this graph? Should I do an example, or is it okay? I mean, this is the prescription of this graph. Okay? So I think instead of doing that, I'll just tell you the theorem. And it's a funny thing. So first we were trying to classify these crystallographic root systems, which came from trying to classify these finite reflection groups. Okay? So the theorem of Cartan and Killing from, I don't know, does anybody know the year of this? Long ago? No. Yeah, so long ago. Classical. This classical theorem of Cartan and Killing says that the Dynkin diagrams, so for every such crystallographic root system, I can define such a graph using this prescription. So the Dynkin diagrams that I get of the irreducible just means, I mean, when I get the graphs, they're in two pieces. I mean, they're not in two pieces, they're just a single graph. Of the irreducible crystallographic root systems, are the things that I actually call Dynkin diagrams. So are those on this board. Okay? And the last theorem I want to, yeah? It sounds circular a little bit. Yeah, so what I mean is that maybe I shouldn't call this Dynkin diagram. So the diagram of a crystallographic root system is this, and the diagrams that you get are exactly these, which now in the literature are called Dynkin diagrams because they classify so many things. Okay, I mean, like, they pop up everywhere in mathematics. Okay, so like I said at the very beginning, this is a little bit unsatisfying because the theorem I'm about to write is that finite type cluster algebras are classified in the same way. Okay? So the theorem by the two people who invented cluster algebras, Fomin and Zelevinsky, in 2003. So remember, there's this series of papers, cluster algebras 1, 2, 3, and 4. So this is in cluster algebras 2. Is exactly sort of the same theorem, but I'm going to spend some time explaining what I mean. It's a little bit subtle. So I'll write the theorem, and then I'll spend some time kind of trying to illuminate the subtleties. A cluster algebra, A sub q, of finite type. A cluster algebra is of finite type if and only if Q is mutation equivalent to a value quiver whose underlying valued graph is one of these. So this word valued is going to be the confusion. Okay. So what do I mean? Okay. So first of all, if I start at the very beginning of the talk, I said, I mean, even in my first talk, I didn't have these valued quivers. I just talked about quivers. Everybody agreed how many arrows were between them, right? So that's the skew-symmetric case, okay? So if I just have quivers, then the cluster algebras that I get that are finite type, in that case, are just the A, D, and E ones. Okay, A, D, and E. So get this one, I get this one, and I get this one. Okay? So this infinite family, and then these are only 3 of them. Okay? So it's E6, E7, and E8, meaning there's one with 6 vertices. So I always have 1, 2, 3, 4 vertices in this configuration. And then I can get 6 by adding 2 more, and I can get E7 by adding 1 more, and I can get E8 by adding 1 more. Okay? So these 3 are called the simply laced Dynkin diagrams, meaning they don't have multiple edges between a vertex. Okay, so these are called simply laced. So the blue are called simply laced. And as I said, if I remove the word valued everywhere, if I'm just doing quivers, these are the finite type cluster algebras. It means that if I start with a quiver and I mutate, and then I get to something where if I remove the orientations of the arrow, it looks like this, then I know that my cluster algebra has finitely many cluster variables. This is what the statement says. Okay. Now in this more generality, in this generality of valued quivers and skew-symmetrizable matrices, this is where the other ones pop up. But it's subtle. Okay? So like, you should not interpret this as, like B2 you should not interpret as 2 vertices and 2 arrows in between. Because I told you the exact opposite occurs in that case. Remember in the first lecture if I said if I had 2 vertices and 2 arrows, that was the 2 Kronecker quiver, and you have an infinite number of cluster variables. So this is not what I mean. Like I said, the value case is a little weird. So what I mean here is that, so let me draw a picture. So this is a great book, by the way. I use this to prepare a lot of the lecture. This is Lecture Notes on Cluster Algebras by Robert Marsh. So if I take these pictures and I instead interpret this as a valued quiver, where this one sees 1 arrow coming out and this one sees 2 coming in, okay? So I don't mean this one sees 2 coming out and this one sees 2 coming in. This is what I mean. Okay? And this one is 2 and 1. Okay, so almost done. And this one is 1 and 2. And this one has 3, so I'm going to write 1 and 3. So what I mean is there's a notion of valued quiver mutation. Okay? And if I can mutate to get some valued quiver that looks like this, then those are also finite type. Okay? So this is what I mean. Okay. So Do I have any more minutes, or is it done? Okay, good. So, yeah. So, okay, good. Thanks. Okay. Any
Questions, please?
Sure. Mm-hmm. Yeah, all of these. Yes. So valued is more general than just a quiver. And I'm saying that if you just have a quiver, you only get the simply laced ones, the ones A, D, and E. And if you happen to have multiple arrows in between, like if not just multiple arrows, but if you have this, not multiple arrows, if you have these valued quivers where one vertex sees a different number of arrows than another one coming in and out, then in that case, the theorem is the same, but you get all of these. You get the ones from before, where the value is the same coming in and out, right? But you also can have, if it can't agree on the values coming in and out, then that's more general, and you also get these. So there's some notion of valued quiver mutation where if you mutate your valued quiver, and then you get to a valued quiver where if you drop the orientation, you get one of these valued graphs, then your cluster algebra from that quiver is of finite type. It's a good point, yes. Yes, yeah. Yeah, so I'll just say what you said again with the microphone so everybody can hear. So what Laurent said is that this classification does not depend on the frozen variables. So all of these quivers that I'm drawing is without the frozen variable. Like if you have some frozen variables attached to your quiver, you don't worry about what's happening with that part. What I mean is that I want the mutable part of the quiver to look like this, to be mutation equivalent to this. And the beautiful part about this, another beautiful fact about this finite type classification is that it's totally independent of these frozen variables or not. No. Two notions of finiteness. So the finiteness I'm talking about in this lecture is finite number of cluster variables. Yes. There's a formula. I mean, yeah, you can say exactly. And I didn't. If I would have had 5 more minutes, I'll just tell you the theorem. So the cluster variables are in bijection with what's called almost positive roots. So these are the positive roots together with the negatives of the simple roots. And there's a nice bijection where the denominators of the cluster variables. So like in the A2 case, we saw something over x1, something over x2, something over x1, x2, and then we had x1 and x2, which you can view as 1 over x1 inverse and 1 over x2 inverse. So those 1 over x1 inverse and 1 over x2 inverse are negative the simple roots. And the other ones, x1, x2, and x1, x2, are the 3 positive roots that occur. So yeah, so there's a bijection between almost positive roots, which is positive roots union the negative simples, and the cluster variables. And the bijection is given in terms of the exponents of the denominator inside these Laurent expansions. What's that? Reflection. I don't know how to. Do you know how to make this precise? Yeah. So. Yeah. So if you just restrict yourself to mutating at sinks, which means all the arrows come in to a vertex, or sources, which means only arrows are only coming out, then you miss the last two parts of mutation don't occur. It only reverses the arrows. And in that case, this happens. Yeah, the diagram stays the same. The arrows just move. What does distinguish mean? It's giving finite type, yeah. But as I said, you don't want to interpret like G2 as 2 vertices and 3 arrows, because that's not finite type. But yeah. So some other people will talk about like where these things occur in geometry, and you'll see that it's kind of funny. Like some of these are coordinate rings of Grassmannians and various things like things to do with SLN and stuff like that. But sort of the numerology doesn't match up. So like something that's for SLN might not be a type A cluster, cluster algebra and so on. But yeah, but people will talk about where they occur kind of in life, yeah, in nature. Yeah, it's a great question, because yeah, these classify simple Lie algebras, and yeah. Like I said, yeah, they classify a lot of things. Yeah, it's a good. Like I said, it's exactly like not what you might think. Like there are things that are very algebraic. Like you take an algebraic group and like like the ring of functions on that thing is a cluster algebra, in some cases, and that thing, like that algebraic group is a certain type, but it's a cluster algebra of a different type. So yeah, I don't. Yeah, it's very strange.
Let's thank the speaker again.
Thank you.